So this is where we left off last time. We were talking about using mod to kind of wrap back around. And the whole point of all this is, this will work in general, but let's take a specific number. If we have an array of size 10, indices 0 through 9 exist. There is no index 10. But you'll notice all numbers less than 10 modded by 10 are unchanged, right? That's really not the right way to say it. The result of modding any number less than 10 by 10 will give you back the original number. 0 mod 10 is 0. 1 mod 10 is 1. 2 mod 10 is 2. And 8 mod 10 is 8. 9 mod 10 is 9. Nothing changes until you hit 10. There is no index 10, right? We want our thing to go back to the beginning. Well, if we add 1 to 9, it becomes 10. 10 mod 10 is 0. Because how many times can you get 10 out of the number 10? Once. What's left over? 0. So remember, it's because all the numbers are less than the thing we're modding it by. As soon as it hits that value, it goes right back to the beginning. It just resets it. Okay? So that's how we're getting this circular functionality here. There's no circle, it's all a linear collection, but because we're modding it by the length of the array, it always goes back to the beginning once it gets big enough if we're always modding. Cool? Any questions about this? This is very important to note. So whenever we're updating the rear, we add 1 to it, but we always mod it by the length. If it resets it to 0, okay, great, it does. If it doesn't, all right, whatever, it doesn't. It doesn't matter. Just adding this little addition of rear plus 1, mod the length of the array. In this example, Q is the length of the array. Q, U, E, U, E. There we go. This is for updating the rear. Would we also need to do this when we update where the front is? Yeah, because it's entirely possible for the rear to loop back, and the front can loop back too. So both would need to loop back. Now, I will take a moment. Okay, with this circular array, can we ever run out of room? Of course we can. Sure, it doesn't matter where the front and rear are, but if there's only 10 spots in that array and I want an 11th thing in my queue, we don't have room. So we will need some form of expand capacity, but obviously it's going to be a little bit more involved than before because the whole front, rear, and whatnot. We can't just use what we did before. We can't just double the size and copy everything over because, well, I'll show you an example in a moment. But before I carry on, I will bring up this warning. This warning is not, I am not talking about what we're talking about, like idea 3 for the array queue. The array, idea 3 for the array queue. Idea 1 was always shuffle everything down such that front was index 0, but the problem was DQs were always linear. Idea 2 was, well, we just kind of we increase where the front is, but we have that wasted space up front. Idea 3 was like a modification in idea 2 where we just, use mod to loop back to the beginning. Idea 3 is, yes, the correct choice in this particular situation. It really is a good decision. And what I'm about to say is really not to suggest that idea 3 is overkill or something. No, idea 3 is the correct decision. But I will take this as an opportunity to point out that sometimes good enough is good enough. Yeah, as you learn more and more complex problems and complex problem-solving strategies, sometimes ease of implementation and maintainability of your code can outweigh the efficiency of your code. In fact, I will always hear stories about this from colleagues, where one of their colleagues is talking about optimizing this thing that runs once in a billion years. And yes, they optimized it, But it was a waste of time. Like, it really didn't matter, right? So these are things that we need to be aware of going forward. This doesn't apply to idea 3. Idea 3 is the correct decision in this particular situation. Better algorithms will always exist. I'm going to do mostly reading of this, but subpar implementations will often do the trick, especially when the problem space is small enough where it doesn't really matter. For example, maybe there is such thing as a linear time algorithm, like a big O of n for one problem, but you have an implementation that's n squared. But we know n's never going to be bigger than like 100, so who the hell cares? Maybe that n squared algorithm that you have took you 2 seconds to write and it's easy to understand. But that linear time algorithm is complex as hell and rather like esoteric. But it doesn't matter. Computational complexity is very important, but sometimes in practice one may, lose the forest through the trees. You get so focused on computational complexity. And I'm guilty of this. Every computer scientist, every programmer is going to be guilty of this. If an algorithm can be changed from n squared to n, you should probably do it. But then again, if the updated algorithm will take a day to implement and it only needs to be run once on a small problem, perhaps n squared is good enough. Even worse, trying to save a few flops. Does anyone know what flop means in the context of computer science programming? It means floating point operations. It's like a unit of how much work a processor is doing. Things will be measured in flops. You save a few flops here and there, it's great and all, but it could distract someone from the more important issue, and perhaps they should just have moved on. Like, if the code is simple but takes a few more flops versus very complex code that saves a few flops, did we really win? And there's a very famous computer scientist, Donald Knuth, a very famous computer scientist, and this is, I'll read the quote. Programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of your program, and these attempts at efficiency actually have a strong negative impact. When debugging and maintenance are considered, we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass up an opportunity in that critical 3%. So obviously we can't make a huge generalization statement about what's always the case. Obviously there's exceptions to the rules. Obviously 97.3%, that's kind of arbitrary. But the point here is, and new programmers will often do this, where you start to think like, oh, I could have made it better. When, well, did you make it better? I'm not saying don't worry about making your code better. That's not what I'm saying. What I'm saying is, and often doing that is a good learning exercise, but my point is it's always a give and take. There's always a balance here. And just be aware of it. All right, to expand capacity, let's say here is our queue. Rear is 1, front is 2. Remember, rear is always going to be the next available spot, just like with the stack, right? Where top was always the next available spot. But front is always where the thing is that we want to remove. Both of which, if we add something, we add it to rear and increment the size. If we dequeue, we remove it from front and increment the front with our mod thing going on. But this could be the case, right? Clearly it's like looping back, right? The order is blue box, black box, green box. If we add another thing such that we have this light blue box, this is now the array. The queue is full. We have 4 things in it, we're happy. If I want to add another thing, we're out of room, we're in trouble. So we need to call expand capacity. But we can't do the old expand capacity we did before. Remember, the old expand capacity was double the size of the array, start at the beginning of the array, and copy all the contents over. We can't do that because suddenly, remember, the front is index 2 and the rear is index 2. So apparently this queue, if we follow the fact that like this is supposed to loop around in the array, we would have a situation where the front of the queue is the blue thing, then the black thing, and then empty, 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 green thing, light blue thing. We have a giant gap in the middle. From indices 4 through 7, we have a problem. The front is index 2, not index 0. The rear is index 2, but if the last thing is the light blue box, which is index 1. It's not index 3, right? Do you see the issue? How we've got this giant gap? So we can't just copy it directly. Really what we would have wanted is kind of like, well, these two, 0 and 1, really should have been like in 4 and 5, right? And 0 and 1 should be empty. Do we see what I mean? No? What's wrong? You went like, no. Yeah. You just moved your head? Okay. All right. So this is an issue. We can't just do what we did before. We have to be a little bit more clever. Now you're probably looking at this problem thinking like, okay, it's not too complex, which is good, right? It's not too crazy, but we need to deal with this situation. So how do we want to do it? Well, we have choices to make, but what can we do? Well, what we can do is just start at the index of the front in the original one and start it and copy it to the index of the front in the other one. But of course, when we're like updating when it needs to loop back, it'll always be based on the size of the respective arrays, the array that's size 4 versus the array that's size 8. Yeah? So start at index 2, go to index 2. Increment 1, mod the length, okay, that's 3. Copy to index 3. Copy to index 4, there is no index 4. We have to copy from index 0 because it loops back. But when we increment the next index here, it's mod 8, meaning it never loops back to index 0. So we're good. So we just have to be careful and be aware that the indices that we're copying from and the indices that we're copying to are not the same thing. They might be the same for the first few, but in general, that's not the case. It's going to change. So we just have to be aware of what we're doing. And it shouldn't be too big of a deal because when we increment to find the next index, it's always add 1 mod the length of that array. Add 1 mod 4. If we were over here, we would say, okay, copy it, like, okay, what's the next index? Add 1 mod 8. So maybe it never looped back. It would go to index 4 over here, where here it would never get to index 4, it would go back to index 0. Yeah? Happy? Sad? Now, there's nothing wrong with doing it this way, such that this is the result. But we can actually simplify the implementation, I think, by not worrying about, okay, add 1 mod the length of the new array. No. I think we can simplify this by always saying, copy from where the front is, and move it into index 0. Copy where, okay, the next one is, mod the length of the array, index 1. Next one is, it actually loops back, index 2. So we will always copy such that it starts at 0, 1, 2, 3. There's no like functional improvement, there's no efficiency to having it copy such that it starts back at the beginning of the array. Really all we're getting is it's a little easier to implement actually. Instead of having to worry about modding the length of this array versus modding the length of that array, no. Just always go from 0 to whatever and start here at front plus 1 mod the length of the array to find the next index. So it would look like this. And this really does simplify the implementation quite a bit. So, okay. This was all just talking about idea 3. So the first question is this correct? Yes, it's going to work. This idea, this implementation, it's going to work. All 3 ideas were correct. They would all work. Idea 1's downside was we always have a linear time DQ. Ideas 2's downside was we're kind of wasting space. And no matter what, after n in queues, we must expand capacity, regardless of how many DQs there were. Where with idea 3, we don't waste the space, and we only ever actually have to call expand capacity after the number of things in the queue hits n, not just after n in queues. And if that was not clear to you, remember, we can have 5 in queues and 5 DQs, and the queue is now empty, right? But with idea 2, we've lost those 5 spots. We can't get them back. We're still 5 units closer to n when we'd have to call expand capacity. So how often will this call expand capacity relative to idea 1 and 2? Well, it should call expand capacity the same number of times as idea 1, but less than idea 2. Either the same or less, depending on specific trials of doing in-queues and DQs with them. So let's implement this. All right, so what do we need? We need an array, fine. We need variables to keep track of the front and the rear. But the magic is all on the in-queue and DQ. So let's have a look. In-queue. Well, in-queue the element. If we're out of space, call expand capacity. Right? We'll look at expand capacity in a moment. But if we're out of room, we call expand capacity. Otherwise, queue at index rear is the element. Update rear, and here on line, what line is that, 45? It's hard to tell for me. 45, you'll see rear gets updated with the method called next index. We'll look at that in a second too. That just does the +1 mod length. I just found it a little easier to make it a private method. Increment size, return true. So this calls expand capacity in next index. Here's next index. You give it some value, it'll give you the current index +1 mod the length of the queue. I just thought it was easier to make it its own method. And then expand capacity. So, I've got old queue, I make a new queue, which is just the length of the array, times 2, a new array of size, the original length times 2. And now watch how I'm doing this. I've got a for loop that starts from 0 to the length of the old queue. I always copy in the new queue to index I, right? We want to start at 0, then 1, then 2, and then 3, and then 4. But I copy from the old front. And then I need to know, well, after we copied something, where's the next thing? Well, that's going to be front +1 mod the length, but we have next index to give me that. So we update front with next index, because front might need to loop back to the beginning of the array, the old array. So far, so good? I'm looking around and I'm still just like, this is what you look like. You all look like this. Now I can't do it with a straight face. But we use next index to get, now here maybe it's a bit of an issue because it's called front. And maybe front isn't the best word to use here. Maybe I should have used another variable name where it's like old current index that I'm copying from. But I'm using front here. So I'm saying front. After I take the thing, think of the old one, right, where the front was index 2. Remember, the order was 2, 3, 0, 1. So front is at 0, or front is at 2. I get the thing from index 2. I get the next index. Front now becomes 3. I copy the thing from index 3. Front now becomes 4, mod 4, 0. And then 1. But now, after we're all done that, considering that we just copied all the stuff from the old array into the new array, the front is always index 0. So set front to 0. And the rear is always going to be, well, what's the size of the queue? The end of the, it's always the size. So after we copy everything over, we update where the front and rear are. Yes?
Would it make sense to implement it like the new Q at index I is just like equal to the old Q, but like just DQ it? Just get valid.
Like you're actually calling DQ, you mean? Well, that would start messing up the size of the class itself. I see what you're saying, but I think you'd run into issues with side effects. And in fact, this is an example. Okay, well, and then in the end, we update what new Q is. Great. Now, there's something about this method I don't particularly love. Can anyone tell me what it is? I'll admit it's not obvious, but you all should be able to see what it is. What were you going to say?
I was going to say front isn't 0 for a point of time.
Okay, that's true. That's not what I'm getting at, but it's connected to what I'm getting at. What I don't like about this, what were you going to say?
Old Q.length, you should use size.
Yeah, that's a good point too. I think maybe I could do that and that would improve its like readability. Yeah, I see what you're saying. But I'm thinking more of like a, I don't know, that was along the lines of the same idea of what I'm concerned about, but there's something else I'm concerned about. Any last ideas? This method, and it's because I was kind of programmed into a bit of a corner. And I got myself into a position where I was kind of forced to program this way. This method has side effects. We don't like side effects. I realize when you have data structures, you're going to have side effects, but this is a private method. Every other expand capacity we've used so far has been a pure function. It takes the old array container and just returns a new version that you just update the field with when you call it. It was pure. It didn't make any changes to the class itself. And this one does that too. It returns the new array that, if I scroll up just to show you my point, expand capacity, the old expand capacities were pure. You gave it the old Q, and then we just updated what that Q reference variable referenced. It was pure, no side effects. And this one is like that too, but it modifies the values of front and rear. A pure function is a function that takes something and returns something based on what it got. Right? It maps inputs to outputs. This function does that. Oh, and it changes some values somewhere else. And that's a side effect. There is nothing inherently sinful about side effects, except that they are often such a big cause of issues elsewhere. We always want our code, if we can, I got to word this carefully, because it's not true. Side effects aren't intrinsically bad, but they tend to cause a lot of issues. If you can, when in doubt, if you can do something with pure functions, which you can always do. If anything you do with pure functions, you can do with like impure functions. Anything you do with impure, you can do with pure. You just have to like redesign things. But in this example, I was kind of in a bit of a corner, and I got stuck, and I was put in a position where I just had to update front and rear. I just had to. I couldn't really, there was no way around it. Yeah?
Could you also just do that outside, like when you call it in that if statement?
Yeah, and that might be like right up here.
Yeah.
Maybe that would be a better place to do it. Because then I can say, look, that now expand capacity is pure. And then you might say, but then that method's impure. Well, that method was already impure. When you add something to a collection, it's going to just modify that thing, right? Sure, this method, it takes some element as an argument, and it returns true, but it did modify the data structure. But data structures are very stateful, and they're often very impure, so it is what it is. And you know what? Maybe you're right. Maybe I should have done that. And that would eliminate the side effects from that other function. And again, you're going to say, yeah, but you just moved where the side effects were. Yes, but one function was already kind of damned to be impure. So I might as well just shove all the shitty stuff in that one shitty method and leave the pure ones pure, right? Pure functions are easier to test. They're less likely to have bugs. We like them.
Yeah, 'cause the purpose of like NQ is like, to update the weird stuff.
Exactly.
Expanding, you just wanted to get the new array.
Exactly. So you know what, so now I'm put in a position where I'm like, okay, every year we talk about this, I go, okay, this is I love this example because it gives me a chance to talk about pure and impure functions, right? But the code could be better if we just did exactly what you said by getting rid of it. But then I wouldn't be able to go on about this beautiful pure versus impure, right? So what do? But I think it's a fun talking point nonetheless. There's nothing wrong if you are writing your functions and you're really stuck and you can't think of a way to do it pure. One, if you're dealing with data structures, it kind of is what it is, right? But in other cases, chances are you could do it pure. No, you absolutely could do it pure. There's no ifs, ands, or buts. You can. But sometimes that's easier said than done. So if you end up writing impure functions, you're not a bad person, but you kind of are a bad person. All right? Try to avoid impure functions. We want pure functions, or methods in this case. Questions about these, though? InQ and its two helper methods we use, the expand capacity and next index. They're both private. They only really matter internally. They don't need to be accessed externally. Yeah. Okay, DQ. All right, well, if it's empty, it's empty. Otherwise, get the element from the front, update the front with that next index method, decrease the size, return the element. If next index changed it such that front looped back to 0, so be it. If it didn't, whatever. It's irrelevant to me. I don't care. The next index managed that nonsense for me. Really, it wouldn't even, I could have just had this line of code. Whatever. Another reason why I like using a private method in this situation, calling next index as opposed to just having this code right here, is yeah, sure, an experienced programmer would look at okay, front equals front plus 1 mod the length of the queue. An experienced programmer would look at that line of code and they would know what it's doing, right? This isn't that outrageous of a pattern. They'd probably come across it in their lives up until that point. But next index, that method name, makes it pretty damn obvious what it's doing. Get me the next index. Another value of having methods is you give name to functionality, which is nice. Now, equals. Equals is a little tricky. So, okay, are they literally the same thing? Check if their classes are equal. If their sizes are not the same, they're not equal. But if their sizes are the same, they're both queues, whatever, now we can start doing the comparison. I've got two variables, two integers. This current index, that current index. It's the front of this and the front of that. Now, what do I have? What's my comment there? Since this and that are the same size, they must be, otherwise we would have broke here, right? If we got past this if statement, this and that must be the same size, meaning it's safe to loop to this dot size or that dot size. It doesn't matter. It's arbitrary. But then I say objects dot equals this dot q, this current index, that dot q, that current index. we can't modify the front fields of each queue. That's going to break the queue. So we need to start at the front, save those values in some other variable, and then modify the values in the other variables by calling this .next index and that .next index. In fact, on lines 48 and 49, does it really matter if I call this .next index versus that .next index? Does it matter? No, it's both. They are not dependent on their instances at all. In fact, maybe I could have made this a static method. It doesn't matter. The next index, this .next index and that .next index are identical. And obviously every method in the classes are identical, but some of those methods might depend on the state of those classes. But these don't. The next index doesn't. It's just return this current index plus this current index mod the length of the queue. Or maybe it does matter. Does anyone have any ideas here? Is it actually important that I'm saying this .next index versus that .next index? Is it possible to have two queues that are equal?
Yeah, like the front can be in a different spot with the same elements in it.
Yeah, but that's entirely fine. But I could have two arrays. I could have a queue with an array of size 10 and a queue with an array of size 1 billion, but they could be equal. And the next index actually does depend on the size of the arrays. Let me go re-show you. Q.length. It's going to depend on the instances Q array, Q-U-E-U-E, lowercase q, the length of that array. Does that make sense? So it is important that I actually specify this and that. So good thing we are. But calling the next index will automatically give you the next corresponding index for each. Like what number comes after this current index and that current index based on their respective array sizes. Yeah? So it does not matter where in the array the contents are. It doesn't matter what the capacities of the arrays are. All that matters is that the elements in order are equal. In fact, it's not even that like the elements in order are equal, because really that doesn't even matter. The order of the elements in the queue don't matter. What matters is that the order of the elements when they come out of the queue matter. But that'll be the same given this implementation, so it's fine. Remember yesterday how I was saying, I don't actually care how it's encoded. All I care about is that, think about it. Just think of the queue as the box. I put the things in the box. When they come out of the box, they better come out in the correct order such that it's a queue. Right? Yeah. So any questions about any of that? All right. Now for another data structure. We talked about stacks. We talked about queues. We talked about linked queues, linked stacks, linked array queues, array stacks, right? We talked about those data structures. Well, now we can have another one, a bag. Now, a bag is going to be very similar to a list that we've seen in Python. There is some nuance difference such that I'm calling them a bag, but we're not going to worry too much about it. Bags are more general. Bags have more flexibility on how we use them, where the things get added, where they get removed from. And we can have different versions of bags too. We can have different kinds of bags. So the high level of idea of what a bag is doesn't really have to be thought of as anything that has to do with any ordering at all. Now remember, when I talk about ordering, there's a difference between them being like, the elements in an array have an order, right? But they might not be sorted, okay? So if I have an array, the fact that A comes before B in an array is meaningful, but that doesn't necessarily mean that A comes before B in some meaningful ordering. Alphabetically it does, great. But having an order versus like being sorted are two different things. And this is going to be important going forward. And another thing too with bag, like think of like a set, right? We use sets in Python very loosely, but we did, right? Or a dictionary, right? We use dictionaries. Now, knowing what you know about these data structures, you know, we've got the interface versus the implementation. Well, how is this thing actually implemented? Well, maybe in the back end it's just an array. An array is this, and an array has an order. But sets themselves don't actually have an order. There's not really an ordering to the elements in a set. A set is just a set of things. There's no actual order. So even though the elements in the data structure might have an order, that might not be meaningful in any way. So if we want to start making a bag, we need to think of, well, with a stack and a queue, we had a way to add things and remove things and like observe it without modifying it, get the size of that collection, and check if the collection's empty. We did that for stacks. It's called push pop peek is empty size. For queue, in queue dequeue first is empty size. So we're going to have the same thing for our bag. We need a way to add things. We need a way to remove things. We need a way to observe things, but leave it alone. Is empty in size. Those will be the same. So given the more general definition of a bag, how exactly we do these things might not be immediately obvious. When I add something to a bag, how should I do it? I mean, at this point, you might be thinking like, well, I mean, it's kind of up to us. Where do we want to add it? With a stack, you added it to the top. Why? Because that was the definition of a stack. When you removed it from the top, because that's what a stack was. A queue, you removed from the front, you added to the rear. Well, how do we want to do it with a bag? Well, depends. When we remove, depends. So the general idea of a bag really is high level. I want this collection where I can put arbitrary elements in and take arbitrary elements out. But how do I want to implement it? Well, we can have a sorted bag, or we can have an indexed bag. And an indexed bag is going to be more like what you're used to with lists in Python. A sorted bag, if we have a situation where the elements that we have to be sorted, let's use a sorted bag. Let's define a data structure called a sorted bag that all elements in that bag must be sorted in some way. Again, there's a difference between the ordering and the sortedness. They're not necessarily the same, but in this case, we want them to be the same. We want the elements to be ordered such that they are sorted by some way. Now, what it means for elements to be sorted remains to be seen. If I give you a bunch of numbers, how would you sort them? That's not a trick question. What would you say? Usually 1 comes before 2 and so on, right? If I gave you a bunch of names, how would you sort them? Probably alphabetical, right? Some things kind of have a natural ordering. If I gave you a bunch of colors, how would you order them? Based on the rainbow? Yeah, I got maybe wavelengths, I guess. I guess we could do it alphabetically too. I don't know. If I gave you a bunch of car parts, how do you order them? Pardon? Serial number? Okay, fine, yeah. The point is, some things have an intrinsic natural order to them, and some, if I gave you a bunch of students, how do you sort them? If I had student objects and I want to add them to a sorted bag, how should they be sorted by? Student ID number? No, I want them sorted by height. That's obviously the most natural ordering. That makes the most sense to me. All right? So sometimes the orderedness, like how things should be sorted, is natural, and sometimes it isn't. Some things are ordinal. They have like this intrinsic ordering to them, and some things aren't. So we'll talk about that shortly. Okay, so unlike a general bag, the specific kind of bag will have an ordering. The ordering of the elements will depend on some characteristics of the contents. And this is important to hear, or important to really emphasize. The elements themselves determine the ordering, or at least the type of the elements themselves determine the ordering. If I have integers, well, the integers have an ordering to them. If I have strings, well, like they have an alphabetical ordering, a lexicographical ordering to them. If I have car parts, well, I don't know. We'll figure that out later. But the elements themselves, the type of the elements themselves determine the ordering, not the sorted bag, not the data structure. The data structure just puts the things in the order that they got to go in, but it doesn't determine the ordering. We can have it kind of determine the ordering by giving it an order, but that's later. But for example, if I gave you the number 58 and I said add it to this collection such that the elements remain sorted, how many options do we have? How many places could this number go? One. Yeah. Where? I know it's a tough one. Between 51 and 67. Why? Because 58 is bigger than 51. But it's less than 67, right? Obviously, if there was a tie, okay, fine, maybe we've got some other cases, but whatever. So here's how I could find the ordering. I can go like, okay, is 58 less than 16? No, all right. Is it less than 23? Is it less than 29? Is it less than 40? Less than 51? Less than 67? It must go there then. And this is actually kind of interesting, by the way. I only ever need to check at any instant if it's less than some value. Because as soon as I know it's less than 67, I know it comes before 67. But I had just concluded an instant before that it's not less than the number that came before it, which was 51. So if it's not less than 51, it must come after 51. But if it's less than 67, it must come before 67. So you only need to check the one number every time. Often I'll see students, new programmers, every time they'll always like check pairs and be like, oh, does it come between? You could simplify it by only ever checking the one on the right. So there's only one way to add the elements. The elements must be added such that they're sorted. It goes there because we know how to count. Indexed bags. This is going to be like lists in Python, right? I can say add this to index whatever. And if I know you probably, like we didn't do a lot of that in Python where we would tell it to add to a list at a specific index. You could have, but we didn't do a lot of that. But if I said, okay, add these elements there, it would mess up the indexing, right? If I wanted to add this to the beginning, well, that would become index 0. This would have to become between 2 and 3. So it should become 3, but we actually added something to index 0, so it should be 4. Yeah, and so on, right? Cool. So this is like the list in Python, an indexed bag. Here we have a choice. With a sorted bag, if I told a sorted bag, add this to the bag, it's got to go find where it belongs. Where with the index bag, I say add it to the bag's going to go where? Where do you want it? I have a choice now. They're different. Yeah, okay. The bag interface that we're going to write is going to be kept very simple. But we're going to write a bag interface. We need a way to add elements, remove a specified element, check if an element is contained in the bag. So now we're adding more functionality. Before we had like push, pop, peek. We're going to add some more functionality. Add, remove, push, pop, enqueue, dequeue. But check if an element is contained in the bag. That's new. But that's just like a linear search or something, right? Count the number of occurrences of an element within a bag. Like, hey, bag, how many 7s are there in you? Right? For example. Check if it's empty, get its size, and get an iterator for the bag. Now, we haven't talked about iterators yet. We will very shortly. We're going to get to a few concrete examples of iterators. But an iterator is a tool that makes it easier to iterate over something. It makes it easier to loop over something. It gives you a common way to loop over a collection, regardless of if it's an array or like a linked structure. Remember, if you wanted to iterate over an array, what would you do? Int I equals 0, I is less than the length of the array, I plus plus, and then you index the array, right? But it was different if you wanted to iterate over a linked structure. Create a reference variable, have it reference the beginning of the linked structure, get the thing, and then say, okay, reference variable equals reference variable dot next, okay, get next. So the way we iterate is very different. An iterator makes it such that it's going to be exact, like the way you do it is identical, code-wise. Yeah?
Is that the thing where it's like for and then like the element and then the code?
Yeah, that's like an enhanced for loop, yeah. But we'll see some examples as we go. There's a couple of ways we can use it, actually. It's kind of neat. That's actually more if something is iterable. And I'm going to give you a warning. It's not that bad, but I will say when we do start talking about iterators, we'll talk about iterators and iterable, and you're going to be like, what? An iterator is like a little robot that iterates over something, right? An iterable, a collection, like a stack, a queue, a bag, a list, will be iterable. But the iterator is a little robot that's like iterating, right? Huge difference, I know. But I'll make it clear hopefully as we go. Let's look at the interface. Add an element, remove an element, check if an element is contained in the collection, count the number of things in the collection, check if it's empty, get its size, and get this iterator. There's my interface for the bag. At this stage, I will say, when you went and looked up a queue, you'd find a Wikipedia article that basically defined the queue to be what we defined the queue to be. I didn't make anything up. A queue is a queue. A stack is a stack, right? But when it comes to a bag, if you go look up a bag, a queue and a stack are so well defined. You look up a bag, the bag's going to be like, I don't know, whatever the hell you want it to be, right? So now this isn't as nice and cleanly and well defined. So when we looked at the interface of a stack and a queue, and you were to say, well, why are those there? It would be because that's what a stack and a queue is. When you look at this bag one, you go like, why is that there? Why didn't you add another method? My answer is going to be like, because I didn't. Why did you have count? Do you really need count? Nah, I guess not, no. So at this point, this is somewhat arbitrary. When I say arbitrary, I don't mean there's no method to the madness. I just mean it's not as formally defined as a stack and a queue was, just FYI. And we'll pick up here on Tuesday.